Section 3.2 Improper Output Handling. OWASP LLM 05-2025, when AI output becomes the attack vector. When developers think about security, they focus on input validation. Sanitize what users send you. Never trust external data. This is correct, but it creates a dangerous blind spot. Developers routinely trust the output of their own AI features without the same scrutiny. An LLM is a black box. Its output might flow into a database query, a web page, a shell command, a template engine, or an API call. If that output is not validated before it reaches those destinations, it is just as dangerous as unvalidated user input, one step removed. The key insight: treat every LLM response as untrusted input from an external system. The model is not part of your trusted code. It is a user-influenced component whose output flows into your application's sensitive operations. Let's clarify how improper output handling relates to prompt injection, because these two are often confused. Prompt injection manipulates what the LLM is instructed to do by embedding override instructions in input. Improper output handling is different. The LLM output is passed unsanitized to a downstream system, causing that system to execute unintended code. This can happen even without adversarial intent. The two often work together. A prompt injection causes malicious output, which the app executes without sanitizing. But regardless of how the dangerous output was generated, the vulnerability is the same: untrusted content reaching a sensitive sink. LLM output flows into 5 categories of security sinks: browsers causing XSS, databases causing SQL injection, template engines causing SSTI, code execution functions causing RCE, and URLs causing SSRF. Let's examine each one. Attack 1. Cross-site scripting via LLM output. Here is a realistic scenario. An e-commerce chatbot retrieves and summarizes product reviews. An attacker posts a review containing a malicious image tag with an on-error handler that steals cookies. The review is stored safely with HTML encoding on the product page. But when the chatbot retrieves it through its API and includes it in a response, the app renders that response as HTML without sanitizing. The vulnerable code sets innerHTML directly to the LLM response. Any scripts or event handlers in the response execute in the user's browser. The fix: use text content instead of innerHTML for plain text output. If HTML formatting is needed, use DOM Purify with a strict allow list of safe tags and no attributes. Always add a content security policy header as defense in depth. The impact includes session hijacking, account takeover through hidden forms, and silent data exfiltration. Attack 2. SQL injection via LLM-generated queries. Natural language database interfaces let users ask questions in plain English, and the LLM translates to SQL. If the generated query is executed via string concatenation, classic SQL injection reemerges. The vulnerable pattern: the LLM generates a SQL query and the app executes it directly. An attacker submits something like show Q3 sales, drop table orders, and the LLM faithfully generates the destructive SQL. The secure approach: never let the LLM generate SQL. Use it only for intent classification and parameter extraction. It classifies the question into a known query type and extracts values. Then execute a pre-written parameterized query that the LLM cannot modify. Research published at ICSE 2025 tested 7 LLMs in LangChain's SQL database chain. All were susceptible. As additional defense, use read-only database credentials for query-only features. Attack 3. Server-side template injection, or SSTI. Template engines like Jinja 2 evaluate expressions inside double curly brace delimiters. This becomes dangerous when LLM output containing those delimiters is placed in the template source rather than as a variable. The vulnerable pattern: an app generates marketing emails with an LLM, then inserts the output directly into a Jinja 2 template string. If the LLM produces text containing double curly braces around config items, Jinja 2 evaluates it on the server, dumping secrets, credentials, and environment variables. The fix: pass LLM output as a template variable, not as part of the template string. The template is a fixed string with named placeholders. LLM output goes into a variable. Variables are always treated as data. Even if the content contains template expressions, they render as literal strings. The impact is severe: secret key exposure and, through Python object traversal, full remote code execution. Always enable auto escape and use a sandboxed environment. Attack 4. Remote code execution via code execution sinks. AI coding assistants and math solvers often execute LLM-generated code. When exec or eval receive LLM strings without sandboxing, the output runs with full application permissions. CVE 2023-29374 rated critical at CVSS 9.8, affected LangChain's LLM math chain. An attacker disguised a shell command as a math problem. The LLM generated Python calling os.system, and exec ran it with full permissions. CVE 2023-37273 affected AutoGPT. LLM-generated Python overwrote the Docker Compose file mounted without write protection, achieving host compromise on restart. The vulnerable code is generate code from the LLM and pass it to exec. The secure approach. For math expressions, use AST parsing to validate only arithmetic operations. Reject anything that is not a constant or basic operation. For general code execution, run it in a Docker container with no network access, a read-only file system, memory limits, and a hard timeout. Impact: full server compromise, lateral movement, and supply chain attacks. Attack 5. Server-side request forgery via LLM-generated URLs. SSRF occurs when an attacker tricks your server into making requests on their behalf. The request originates from inside your network, bypassing firewalls. When an LLM generates URLs that the server fetches, an attacker can redirect requests to internal infrastructure. Cloud metadata endpoints like 169.254.169.254 are reachable from within the server but not from the internet. An attacker who causes the LLM to output that URL gains access to IAM credentials, granting access to S3 buckets, databases, and other services. The vulnerable code fetches whatever URL the LLM returns without validation. The secure approach has 3 layers. First, validate against an allow list of permitted hostnames. Second, resolve the hostname and reject any IP in private, loopback, or link local ranges. Third, disable redirect following because attackers use redirects to bypass hostname validation. Impact: IAM credential theft, internal network scanning, and exploitation of local host-only APIs. Let's walk through a real-world case study from Portswigger's Web Security Academy showing how these attacks chain together. The attacker identifies that a chatbot reads product reviews through an API. They post a review containing a hidden iframe payload. The application stores it safely, HTML encoded, displaying as literal text on the product page. Then the victim asks the chatbot about that product. The LLM retrieves the raw review text through the API, includes it verbatim in its response, and the chat UI renders it with innerHTML. The iframe executes in the victim's browser, loads their account page, and submits the delete account form. The critical lesson: the review was safely encoded on the product page. The vulnerability existed only in the LLM output path, a completely separate code path the developer never considered for XSS protection. 2 features sharing the same data, one unsanitized output path, and the entire defense collapses. There is another dimension to this vulnerability. An analysis of 2,500 PHP websites generated by GPT-4 found that 26% contained at least one exploitable vulnerability, with XSS being the most prevalent. This has nothing to do with prompt injection. The model simply generates insecure code patterns that developers accept and deploy without review. AI-generated code carries the same risk as code from an unverified source. The vibe coding workflow, where you ship whatever the AI produces, is the most direct path to introducing these vulnerabilities. Now let's talk about the architectural solution. OWASP recommends a centralized output validation layer, a single function through which all LLM responses pass before reaching any downstream system. One validation point means one place to update, test, and audit. The pattern works like this. You create a validator that accepts the LLM response and the output context, meaning where the text is going. It first checks for suspicious patterns, logging them for security monitoring. Then it applies context-appropriate sanitization. For HTML, it applies entity encoding. For SQL parameters, it rejects SQL keywords. For templates, it escapes curly brace delimiters. For logs, it strips new lines. For API parameters, it URL encodes the output. This prevents the common failure mode where one output path is protected, but another is not. Here's your sync-by-sync defense reference. For HTML, use text content by default, DOM purify if HTML is needed, plus a CSP header. For SQL, use intent classification with parameterized queries. For templates, pass output as a variable with auto escape enabled. For exec and eval, avoid them entirely. Use AST validation for math and Docker sandboxes for code. For shell commands, use fixed command templates with typed parameters. For URLs, validate against hostname allow lists, block private IPs, and disable redirects. For logs and email, strip new lines and use fixed template structures. And here is your practical checklist before shipping any LLM-powered feature. 1. Where does the output go? 2. Does any sync execute or interpret it? 3. Can user input influence what the LLM outputs? 4. Are you applying zero trust to LLM responses? And 5. Have you tested with adversarial inputs in your CI/CD pipeline? Remember the core principle: treat every LLM response as untrusted input. Apply context-aware encoding, parameterization, and sandboxing, the same defenses you apply to user-submitted data. The model is not part of your trusted code. In the next chapter, we will cover system prompt leakage, where attackers extract your application's secret instructions from the LLM. For more details on all these topics, visit wisebuilder.dev.